Hi everybody, I hope this video finds you well. In today's video, we're going to be moving into section 11.4 of your textbook, which introduces us to the next major technique we're going to have for analyzing the behavior of infinite series. This next major technique is going to be sort of under the umbrella sort of title of comparison tests. These comparison tests allow us to sort of compare a series that we're analyzing against a type of series that we already know the behavior of and use that to deduce if our series converges or diverges. So far, we've learned how to analyze series through either understanding them as a particular special type of series, geometric, telescoping, p-series. We've seen that we have this test for divergence that analyzes the behavior of series through the limit of the sequence. And in section 11.3, the very last section, we saw that sometimes we can analyze series through comparing them to improper integrals. Now, since we've established some results about certain types of series, specifically geometric and p-series, what we'd like to be able to do is compare a series we're working on to one we already know information about. And we're going to learn two ways to do that. For the first part of this video, we're going to be focused on what is called the direct comparison test, which is a very important sort of theoretical or conceptual idea. And then in the second half of the video, we'll be taking a look at the limit comparison test, which is very useful computationally. So let's get in and take a look at these different tests. So the direct comparison test here says, suppose you have two series. So we have series n equals 1 to infinity of a sub n and the sum from n equals 1 to infinity of b sub n. And really the only condition is that they both have to have always positive terms. So all of the terms of the sum have to be positive. And we're going to put the second condition that the terms from this series are always larger than the terms from this series. So you can sort of think about it in my notation that the series a sub n is the larger series and the series b sub n is the smaller series. Then if we have these always positive terms and the fact that the terms of this series is larger than this one, then we get the following two statements to hold. If the series sum from n equals 1 to infinity of a sub n converges, so does the sum from n equals 1 to infinity of b sub n. So you can sort of think about that as saying that if the larger series converges, then the smaller series converges. And if the sum from n equals 1 to infinity of b sub n diverges, so does the sum from n equals 1 to infinity of a sub n. So you can sort of think about that as saying if the smaller one diverges, so does the larger one. So we've got two things to sort of prove here, and I'd like to sort of go through and look at both of them. So to start off with, we're going to prove the first statement. So we're going to assume that the sum from n equals 1 to infinity, a sub n, converges. Okay, so let's go ahead and let's just let s sub k be the sum from n equals 1 to k of a sub n. So in other words, we're letting s sub k be the partial sums for this series. So since this converges, that means so the limit as k goes to infinity of s sub k equals some value L. So that's what it means for the series to converge. That means the partial sums, the limit of the partial sums actually is a finite value. All right, now consider the other series. So sum from n equals 1 to infinity b sub n. Let's go ahead and let t sub k be equal to the sum from n equals 1 to k of b sub n. So we're letting these t sub k's be the partial sums of b. The first thing that we'd like to notice is that t sub k is always going to be less than or equal to s sub k, right? T sub k is always less than or equal to s sub k, since b sub n is always less than or equal to a sub n for all n. That should make sense, right? If the terms b sub n are smaller than the terms of a sub n, then summing up all the b's is always going to be less than or equal to summing up all the a's. So what this tells us is if t sub k is always less than s sub k and s sub k goes to L, well then t sub k is always less than or equal to L. Right? If the infinite sum eventually goes to L, then the finite sums all have to be less than L. Why do we care about that? Well, this means that t sub k is bounded above by L. Now, this probably already gives away to you guys how we're going to finish up this proof. When we start to talk about bounded above, that sounds like we're gearing up to use the monotonic convergence theorem. And we are. We've now shown that T sub k, the partial sums of the B sub n series, are bounded above. Do we know that they're monotonic? Well, for sure. Since B sub n is always greater than 0, all the terms are positive, that means T sub k is strictly increasing. Why is that? Well, if the terms are always positive, then adding more and more of them is always going to make your partial sum get larger and larger. So T sub k is bounded above, and T sub k is strictly increasing. So by the monotonic convergence theorem, T sub k converges. Thus, we can say that the sum from n equals 1 to infinity of B sub n converges. Because what does it mean for a series to converge? It means the limit of the partial sums converge. Okay, so we've proven the first direction. If the large one converges, then the smaller one converges. Okay, let's go ahead and give ourselves another page, and we're going to prove the second piece, that if the smaller one diverges, so does the larger one. So we're going to use the same sort of setup. So we're going to assume that the sum from n equals 1 to infinity B sub n diverges, and we're going to let T sub k be equal to the sum from n equals 1 to k of those B sub n's. So we're going to let the T sub k's be the partial sums. Now, again, when things diverge, that could mean a lot of things. That could mean that the sum is going to positive infinity. It could be going to negative infinity. It could be oscillating. The limit could not exist. But in our situation, we know that none of those are, only one of those is going to be the case. Since the terms are always positive, since B sub n is strictly greater than 0, and sum n equals 1 to infinity, B sub n diverges, this implies that T sub k is actually headed to positive infinity. Well, how do we know that? Well, again, if the B sub n's are always positive, then as you're adding things, it's just getting larger and larger. It can't be headed to negative infinity, and it can't be oscillating, right? It can't be bouncing up and down because, again, it's always just increasing. So if you're always increasing but you diverge, there's only one place you could be headed, and that's positive infinity. So we know T sub k is headed to positive infinity. Now, if we consider what we're actually trying to analyze, n equals 1 to infinity A sub n, let's go ahead and let S sub k be the partial sums there. Okay, so if we let those be the partial sums there, then of course these partial sums are always larger than this. So since A sub n is always greater than or equal to B sub n, this implies that S sub k is always greater than or equal to T sub k. So we know that S sub k is always greater than or equal to T sub k, but we know T sub k is headed to positive infinity. So since T sub k is headed to positive infinity, so is S sub k. It's headed to positive infinity as well. So what does that tell us? Well, that tells us, so sum n equals 1 to infinity, A sub n diverges. So what we've just proven is if the smaller one diverges, then the larger one diverges. So there we go. That's the direct comparison test. So the direct comparison test, in a lot of ways, it tells us exactly what we would expect. It tells us that as long as things are always positive, that if you are larger than something that diverges, you too will diverge. And if you are smaller than something that converges, so if you're smaller than something that is finite, you too will be finite and you will converge. The problem computationally with the direct comparison test, I mean, theoretically, this is a great idea. The computational issue is actually showing that the terms of one series are always greater than or equal to the terms of the other series. That can sometimes be quite hassle-some. So we're going to take a look at a couple examples of using this direct comparison test to analyze the behavior of series, but then we're going to look at sort of a follow-up called the limit comparison test, which turns out to be computationally much easier to use. So let's take a look at a couple examples. So for our first one here, we want to determine if this series converges or diverges. We have the sum from n equals 3 to infinity, ln of n over n. So what I'd like to do is, just for a little bit of practice, let's start by trying our most basic approach to analyzing the behavior of a series. So we got to go ahead and try the test for divergence. So the test for divergence means that we want to apply the limit as n goes to infinity of ln of n over n. We want to see what happens to these terms. This is something where we would probably want to apply L'Hopital because we have an infinity over infinity, and they're different types of functions. Here, this is a logarithm. This is a polynomial. So let's go ahead and replacement theorem that so that we can go ahead and use L'Hopital. So we have ln of x over x. Then we can L'Hopital that. We have the limit as x goes to infinity, 1 over x over 1. And it should be clear that that's equal to 0. So unfortunately, that gives us no info. Why is that no info? Because again, what that means is that in the long run, these terms get really, really close to 0. So they're not quite 0, but they're very close to 0. And we're adding up an infinite amount of them. Adding up an infinite amount of infinitesimally small things, that's again the balancing act where we don't know if that's going to converge or diverge. If this had been anything else, we could have just concluded immediately that this was going to diverge. Okay. So let's think about whether or not we could approach this in a way from a previous sort of video. Previously, we learned about the integral test. So let's try that. So let's try the integral test. So we would probably let f of x be equal to ln x over x on this 3 to infinity. Is this going to be continuous? Well, for sure, the only place that this would be non-continuous is if we started getting into the negatives or 0 or something. Is it going to be positive? Well, ln and x are both going to be positive on 3 to infinity, so we're all good there. And is it going to be decreasing? Well, unfortunately, this and this are both increasing, so the denominator is getting larger, but so is the numerator, so we need to probably use the derivative. If we take a look at the derivative, we'd get 1 over x times x minus ln x times 1 over x squared. And if we simplify that, we get 1 minus ln x over x squared. Now, certainly the denominator is always positive, and 1 minus ln x, well, once x is greater than e, this is going to be negative. And of course, we're on 3 to infinity, so we're beyond e. E is about 2.7. So this is guaranteed to be less than 0. Since the derivative is always less than 0, that does mean that it is decreasing. So all the conditions for the integral test apply. So what we could try to do is consider the improper integral from 3 to infinity of ln x over x dx. And of course, the first thing we would do is treat that as a limit as t approaches infinity from 3 to t of ln x over x dx. Then we'd have to think of a way to integrate this. Well, we could say, let's try to do u equals ln x, since the derivative du equals 1 over x is right there. So let's try that. U equals ln x, du equals 1 over x dx. That's exactly what we have there. We'll need to change our bounds, though. Our original bounds were t and 3, and our new bounds are going to be ln of t and ln of 3. So we would get the limit as t goes to infinity, the integral from ln of 3 up to ln of t, and this whole thing would just turn into u du. Then we could integrate that very simply using power rule, and we could get 1/2 u squared evaluated from ln of 3 to ln of t. Okay, then we could plug that stuff in, and we'd get 1/2 ln of t squared minus 1/2 ln of 3 squared. Okay, so we finished our definite integral. Now we just need to evaluate the limit. Obviously, this limit is only going to apply to this term. As t goes to infinity, ln of t slowly goes to infinity, but it does go to infinity. Squaring that is still going to head towards infinity, so this is going to head towards positive infinity. So we would say, by integral test, this series diverges. Okay. Well, this is sort of interesting. I thought we were learning about comparison tests, but we just went ahead and did this as an integral test. But notice it took quite a bit of work to do this as an integral test. As an integral test, we had to come up with a function. We had to make sure that the function satisfies all three conditions of the integral test. Then we had to consider the improper integral. Then we had to rewrite the improper integral as a definite, it was a limit of a definite integral. Then we had to figure out how to actually get the antiderivative, and then we had to evaluate the limit. Let's see a much easier way to approach this using our new comparison test. So let's give ourselves the same thing here. So let's try this direct comparison test, which we'll often abbreviate as DCT. So let's recall that the sum of 1 over n, and sometimes when I'm doing comparison tests, I'll just sort of omit the starting spot and the infinity, because just as a sort of shorthand notation. So recall that the sum from 1 over n is a divergent p-series, because this is p equals to 1, which is less than or equal to 1. This is something we actually showed using integral test. And in fact, in section 11.3, we said that the sum of 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. So this sum 1 over n is a divergent p-series. It's p equals 1. But you should just note that ln of n over n is always greater than 1 over n, right? At least for n greater than or equal to 3, right? I mean, that's what we're working on. So for n greater than or equal to 3, ln of n is always just greater than 1 over n. I mean, ln of n gets larger and larger. So the terms here are always larger than the terms here. But this series is a divergent series. So that means that our series is larger than a divergent one, which means it must also diverge. So by direct comparison test, sum n equals 3 to infinity, ln of n over n also diverges. And that's a lot easier. That's just recognizing that every one of these terms is automatically larger than every one of these, so that means it must also diverge. So again, just sort of like integration. When you were first learning about integration, you learned that there were usually several ways you could get to the same answer. Same thing here with diagnosing series. We could analyze this through an integral test, as we did here, or we could analyze it a little bit faster with a direct comparison. The next couple examples we're going to do are all going to just be direct comparisons, just to get more practice with that. But again, sometimes, you can approach these things in several different ways. Okay, let's go ahead and take a look at another one. So for this one, we've got the sum from n equals 2 to infinity, 3n minus 4 over n cubed plus 8. So we're going to try to use this comparison test. So the first thing I'm going to try to do is just think about what am I going to compare it to. If we sort of look at this, our idea would probably be that in the long run, what's going to really matter here? Well, in the long run, in the numerator, is that minus 4 going to matter? Well, as we go towards infinity, that 3n is going to be far more important than the minus 4. So we'd probably guess that the numerator is going to be similar to 3n. And in the long run, that n cubed plus 8, does it matter that we're adding 8? Probably not. It's going to be just similar to n cubed, which if you simplify is sort of like the sum of 3 times 1 over n squared. And of course, that 3 you could just stick out front. That's sort of similar to 3 times the sum of 1 over n squared. So what do we know about that? Well, this right here, this is a p-series that converges. How do we know that? Because we have p equals to 2, which is greater than 1. So we're sort of saying that this thing, in the long run, should sort of be similar to a convergent p-series. Now we can try to use direct comparison. So to use direct comparison test, what we have to show is we have to show that the terms here are smaller than the terms here. We've got to show that the terms are smaller because this is convergent. So the only way we'll get information is if we can show that this is smaller than something that converges. So we can write that out. We can say we need to show that 3n minus 4 over n cubed plus 8 is less than or equal to 3 over n squared. And we get to keep that 3 because, again, the 3 isn't going to have any impact on the behavior there. This should feel very familiar. We did these similar ideas when we were doing the comparison test for improper integrals. As we know, there's a very strong connection between improper integrals and series, so it's not a surprise that this feels very similar here. So what does our actual proof look like? Well, we start with 3n minus 4 over n cubed plus 8. If we delete that minus 4 up there, well, certainly we'd get something that's larger, 3n over n cubed plus 8. And if we delete that plus 8, we're making the denominator smaller, which makes the overall fraction larger. So we'd be safe in saying this. And then, of course, if we simplify that, that's 3 over n squared. Check. So at any value of n, 3n minus 4 over n cubed plus 8 is less than or equal to 3 over n squared. You can try that. If you want, pick out an n value like n equals 10. Plug it in here. You're going to get like 30 minus 4 over like 1,000 plus 8. Type that into your calculator and compare that to 3 over 10 squared. You're going to see that this is smaller than that. That's what we've just shown. We've shown that that always holds. So why is that important? Well, that means the terms here are smaller than the terms here. This series converges, so it sums up to a finite value. So this one must also sum up to a finite value. So by dct, and since the sum of 3 over n squared converges, so does the sum n equals 2 to infinity, 3n minus 4 over n cubed plus 8. So we've just shown that this one is a convergent series by comparing it against another convergent series. Okay. As we sort of mentioned, a lot of times, in just a few moments, we're going to talk about another type of comparison test, which is even easier because it avoids having to do this sort of string of inequalities. But my last couple examples of direct comparison focus on one thing that direct comparison is really, really good for. And the best thing direct comparison is used for is when you are working with bounded functions. So let's take a look at that. So we're going to try to determine if the following series converges or diverges. We have the sum from n equals 2 to infinity of 6 minus sine n over the square root of n. And by bounded functions, sine of n, cosine of n, arctangent, arcsine, arccos, those are all great examples of bounded functions. They're functions that live in a certain range. So how does direct comparison sort of help us here? Well, the idea is that we're going to think that this is sort of similar to, well, that sine of n is going to bounce around between minus 1 and 1, but it's not going to stray too far. It can't drift off towards like infinity or anything. So when we do 6 minus sine of n, that's got to just bounce around between a set of numbers. So this is sort of going to be similar to a number over the square root of n. And of course, that number isn't going to impact the behavior because it's just some finite number. So we know that this right here is a divergent p-series. How do we know that? Because the p here is 1/2, which is less than or equal to 1, because of course square root of n is just n to the 1/2. So we expect that this thing will also diverge. So how do we actually show that? Well, if we're going to compare it against something that diverges, our hope is to show that this is larger than this. So we need to show that 6 minus sine of n over the square root of n is greater than or equal to some number over the square root of n. Well, let's see how we can do that. We can say 6 minus sine of n over the square root of n is greater than or equal to. Well, what can we say about that 6 minus sine of n? Well, sine of n is always between minus 1 and 1. So this thing here, if we do 6 minus 1, it could be as small as 5, and 6 minus negative 1, it could be as big as 7. So this 6 minus sine of n lives between 5 and 7. We want to say something that we're assured that this is greater than or equal to. So we could put 5. We know 6 minus sine of n is never going to be smaller than 5. It's always 6 minus sine of n is always going to be greater than or equal to 5. Keep our square root of n, we're not modifying that at all. And notice that that is a number over the square root of n. Specifically, it's the number 5. So we know that 6 minus sine of n over root n is always greater than or equal to 5 divided by root n. So by direct comparison test, and since the sum of 5 over root n diverges, so does the sum n equals 2 to infinity 6 minus sine of n over root n. So we've just shown that this thing diverges. And the whole idea is that while the numerator is not actually approaching 5, that's definitely not true. The numerator is actually cycling through values between 5 and 7. So it's going through a bunch of values between 5 and 7. The idea is that even if the numerator was always just 5, which is as low as the numerator ever goes, this thing would still diverge because the sum of 5 over root n, which is guaranteed to be smaller than this, would diverge. That would sum up to an infinite value, so our thing must also sum up to an infinite value. All right, let's do one last direct comparison and then move on to the limit comparison test. So we want to determine if this series converges or diverges. Notice that once again, we have that sort of bounded function 2 cosine n. So let's think about what this would look like. If we think about in the long run, this 5 plus 2 cosine n, that's just going to bounce around between different numbers. So this is probably going to be like a number over 3 to the n, which if you wanted to, I guess you could think about that as sort of a number times 1 over 3 to the n. Now, 1 over 3 to the n is not a p-series. It's not n cubed. But you could think about that as the sum of like a number times 1/3 to the n. And that is something we know. That's not a p-series, but that's a geometric series. This converges as a geometric series since absolute value of r would be 1/3, which is less than 1. So our expectation is while this thing is bouncing around between different numbers, it's never straying too far. In fact, we sort of know where it's living between. It's going to live between 3 and 7 because cosine drifts between -1 and 1. So 2 times cosine is going to drift between -2 and 2. Adding 5 to that means that this thing up there is sort of living between 3 and 7. So this is always some number between 3 and 7 divided by 3 to the n. That should act a lot like the geometric series that we know converges. So let's try to use our direct comparison test. So what do we need to show? Well, if we plan on showing something converges using direct comparison, we need to show that this is smaller than this. So we need to show that 5 plus 2 cosine of n over 3 to the n is less than or equal to some number over 3 to the n. So how would we do that there? Well, to actually prove that, we'd say 5 plus 2 cosine n over 3 to the n. We know that that's going to be less than or equal to. We said that this sort of lives between 3 and 7. So since we're trying to figure out something that is strictly greater than it, let's use the 7. So we'd say 7 over 3 to the n. And notice that that is a number divided by 3 to the n. So we're all good. That tells us, so by dct, and since the sum of 7 times 1/3 to the n converges, so does the sum from n equals 1 to infinity, 5 plus 2 cosine n over 3 to the n. So we've just shown that this thing is also going to converge because it's always going to be smaller than this geometric series, and we know that this geometric series sums up to a finite value, so our series must also sum up to some smaller finite value. Do we know what that finite value is? Well, we could figure out what this one is by using like the geometric series formula, but that's not going to help us know what this one is. We only know that the sum of this one is smaller than the sum of that one, but that is good enough to say that it converges. Okay, so as you can sort of see from these past couple examples, I'm just going to go back real quick to them. On all of them, they sort of hinged on coming up with this inequality. Here we had this one we had this whole chain of inequalities. Here we had this sort of simpler one based on the bounded function. Same thing here, we had a slightly simpler inequality based on the bounded function. But with direct comparison, you have to have that inequality to establish the use of that theorem. Inequalities can be a little bit hassle-some. Notice that if we had been back, say, on this one here, this would have failed if we had simply had 3n plus 4 instead of 3n minus 4, because we wouldn't be able to say that 3n plus 4 is less than or equal to 3n. That's not true. But it doesn't seem like it should really matter if it was a minus 4 or a plus 4 or whatever, yet we wouldn't be able to use direct comparison. And that's the limitation of direct comparison. For direct comparison, you have to directly show the inequality holds. Luckily, there's a slightly more advanced technique called limit comparison, which makes the computational side, actually evaluating things, much easier. So let's talk about that. So the limit comparison test, this one, very, very powerful. This is going to be one of the ones we use the most. So we'll give this some stars here. So the limit comparison test basically says that if you have two series, again, a sub n and b sub n, and they always have to have always positive terms, so we have that same condition. But instead of having to show that a sub n is always strictly greater than or equal to b sub n, what this says is if you can show that the limit as n goes to infinity of the ratio of the terms, an over bn, is equal to L, where L is a finite non-zero value. So if you can show that the terms, the ratio of the terms, have a finite non-zero limit, then both the series either converge or both series diverge. In other words, if you can show this, then you automatically know that these two series have the same behavior. They either both converge or they both diverge. What's the explanation for this? Well, your book gives a pretty formal proof. It's not totally formal though, and I don't know if this one really requires a completely formal sort of idea here. What this is really sort of saying is that if these terms in the long run approach a value of L, what that basically means is that one of the series is basically a scalar multiple of the other. It's just like the other one times whatever that L value is, at least in the long run. And what that basically means is that if one of them converges, if that's a finite value, then the other one is a scalar multiple of a finite value, which is also finite. If one of them diverges and heads towards infinity, the other one is some number times infinity, which also diverges. So they seem that they have to act the same, provided that the terms really go to some finite non-zero value. So that at least gives you guys a little bit of an explanation. More formally, what they actually do in your textbook, if you want to try to follow along, is what you can do is you can prove this using direct comparison test. So what you do is you argue that an over bn gets very close to L, and then you can use that to actually create a direct comparison between these two. If you want, you can read that in your textbook. Otherwise, I'm more interested in making use of this limit comparison test. So let's go ahead and take a look at some examples of actually doing this. All right, so we've got another one here. Sum from n equals 1 to infinity, 4n to the 2/3 minus 3 over 5n minus 4. The idea of limit comparison is we're still going to basically just come up with something that it should be similar to. So I'm going to say that this, and now you can really sort of get loose with just sort of forgetting anything that's not going to be the most dominant term. In that numerator, probably the only thing that's going to matter is that n to the 2/3. And in the denominator, the only thing that's going to matter is n. Notice that that would be the same as the sum of 1 over n to the 1/3. And we know that this diverges as a p-series because we have p equals 1/3, which is less than or equal to 1. So our guess is that this thing should roughly be similar to this divergent p-series. So let's try this limit comparison test. To do the limit comparison test, you need to take the limit as n goes to infinity of the terms of this series divided by the terms of this series. So 1 over n to the 1/3. Then you'll notice that you have this sort of complex fraction, fraction over fraction. So let's flip this up and put it up here. So we get the limit as n goes to infinity. We get 4n minus 3n to the 1/3 over 5n minus 4. Now we have our sort of standard expression. We did a lot of limits like this. Notice that this is not a series right now. This is just a limit. So you can use any of your standard limit tricks. So 1 over n, 1 over n. Limit n goes to infinity. 4 minus 3 over n to the 2/3. 5 minus 4 over n. This and this clearly go to 0. So this is equal to 4/5. What do we care? What do we want about this sort of number here? Well, we want this to be finite and non-zero, which it absolutely is. What we're basically saying is that in the long run, these guys here, these numbers, are about 4/5 times these numbers in the long run. If you want, on your own, try like n equals 1,000, plug in n equals 1,000 here, plug in n equals 1,000 here. What you'll see is that what you get over here is roughly 4/5 of what you get here. Or in other words, 4/5 times this thing should give you roughly about that there. Okay. So there we go. We've now shown that the limit comparison test does hold because we got a finite non-zero value. Sorry, just to go back, I think I misspoke there now that I'm sort of remembering what I said. When I said that this is 4/5, if you plug in about n equals 1,000 into here and into here, then what you get over here should be 4/5 of what you got here. Excuse me, I think I said 4/5 of that guy. That would be backwards. This is 4/5 of this guy is roughly that one in the long run. So again, for a really large n value. So since we got a finite non-zero value, our limit comparison test holds, which means that since this one diverges, this one also diverges. So by LCT, and since the sum of 1 over n to the 1/3 diverges, so does our series sum 4n to the 2/3 minus 3 over 5n minus 4. And you'll notice that I'm going to start, when I'm just talking about behavior, dropping the start and the infinity, because we're just saying that series diverges. That's totally fine for notation. Okay, let's try another one. So we want to determine if the following series converges or diverges. We have the sum from n equals 2 to infinity, 2n squared plus 5 over n to the 4th plus n cubed minus 1. Same idea, we're just going to lop stuff off and talk about what's going to be the most important. Up top, the most important thing should be n squared. On bottom, the most important thing should be n to the 4th. That means that that looks like it's going to be about 1 over n squared, and we know that this converges as a p-series, since p equals 2 is greater than 1. So we expect that this is roughly the same as this convergent p-series, so we expect that this is going to converge. How do we show that? Well, we do this LCT. We do the limit as n goes to infinity, 2n squared plus 5 over n to the 4th plus n cubed minus 1, divided by 1 over n squared, and we need to show that this limit is finite and non-zero. So let's flip up that n squared, and we get the limit as n goes to infinity, 2n to the 4th plus 5n squared over n to the 4th plus n cubed minus 1. Then we do our standard trick, 1 over n to the 4th, 1 over n to the 4th. That looks like we're going to get the limit as n goes to infinity, 2 plus 5 over n squared, 1 plus 1 over n minus 1 over n to the 4th. This, and this are all going to go to 0, so this is going to equal 2. What we care about is that it's finite and non-zero. Check. So that means that the terms here for really large n are about double the terms here. So if you want, try plugging in like n equals 1,000 into both of these. What you get over here is going to be about twice of what you got here. So the terms over here are about twice as big as this. So this guy converges to some finite value, so we would expect this one to converge to some finite value. So we would say since, or by LCT is usually how we phrase it, so by LCT, and since sum 1 over n squared converges, so does our series. Sum n equals 2 to infinity, 2n squared plus 5 over n to the 4th plus n cubed minus 1. So we know that this is a convergent series because it should act the same as 1 over n squared. Notice that LCT is much more efficient than the DCT because you don't have to worry about any sort of messy bounding or inequalities or anything. You just have to be able to evaluate this limit. You'll notice also that when we've been doing these comparison tests, both direct comparison and limit comparison, one key thing that goes sort of unmentioned, but it should be noted, is that we have to compare against something that we know the behavior of. And really, the only two types of series that we know the behavior of comprehensively are geometric series and p-series. So you'll notice that every time we do this, we're basically comparing against something that's either geometric or a p-series, because those are the only two that we know the general behavior of. Okay. Let's wrap this up with a couple more examples. So we're going to try to determine, again, if this series converges or diverges. You'll also notice that everything we're doing always has positive terms so that we have that condition met. If for some reason some of these had negative terms, or later on, like when we move into like 11.5 and beyond, we'll sometimes see alternating terms which have positives and negatives. You wouldn't be able to use any of the stuff that we're talking about here. But for all the ones we're seeing right now, everything's always positive, so these comparison tests are a valid approach. So let's go ahead and think about what we would do here. We probably think that this is roughly the same as the square root of n squared, right? That plus 1 probably doesn't matter. And down bottom, probably also just n squared, because again, that minus 2 shouldn't matter. So notice that that would be roughly the same as n over n squared, which would be the same as 1 over n. And of course, we know that this diverges as a p-series. because we have p equals 1, which is less than or equal to 1. So we expect that this thing is about the same as this, so we expect that this is going to diverge. To actually show that, we'll do our LCT. We'll do our limit as n goes to infinity, n squared plus 1 over n squared minus 2 divided by 1 over n. Okay, let's flip this n up top, and we get the limit as n goes to infinity, n square root n squared plus 1 over n squared minus 2. Okay, let's choose out the largest power in the denominator, which is that n squared. So let's multiply by 1 over n squared, 1 over n squared. If we do that, we should get the limit as n goes to infinity. Here, the 1 over n squared is going to cancel with the 1 over n, and I guess we'll get 1 over n times the square root of n squared plus 1. And in the denominator, we'll get 1 minus 2 over n squared. Now, we'd like to simplify this a bit. Notice that you can think about the 1 over n as the square root of 1 over n squared. So in other words, it can come inside the radical as a 1 over n squared. So we get the limit as n goes to infinity, square root 1 plus 1 over n squared over 1 minus 2 over n squared. Then, of course, this goes to 0, this goes to 0. So that looks like we get 1, which is finite and non-zero. So that's exactly what we wanted. So that means the LCT does apply. So we could say by LCT, and since the sum of 1 over n diverges, so does the sum square root n squared plus 1 over n squared minus 2. So in other words, these terms are about the same as these in the long run. So since this sum diverges, so does this sum. Okay, let's take a look at one last one where we won't be comparing against a p-series, but the same idea holds. So we're going to try to determine if this series converges or diverges. Sum from n equals 2 to infinity, 2 to the n plus 7 to the n over 9 to the n minus 3 to the n. Now, this, of course, is not going to be similar to a p-series, but we can use the same logic. We can say that this should be roughly the same. Clearly, up top, the 7 to the n is going to matter a lot more than the 2 to the n. And in the denominator, sure, you're subtracting 3 to the n, but the 9 to the n is going to be so much more important. So it's going to be similar to 7 to the n over 9 to the n, which, of course, is the same as 7 over 9 to the n. And what is this? All right, well, let's circle the whole thing. Well, this is not a p-series, but it is a geometric series. This is a geometric series, r equals 7 over 9, which in absolute value is less than 1, so this converges. So we expect that in the long run, this is similar to this convergent geometric series. So let's try to use the LCT to show that. So for the LCT, we're going to take the limit as n goes to infinity, and we'll take the terms 2 to the n plus 7 to the n, 9 to the n minus 3 to the n, over 7 to the n over 9 to the n. Now this is pretty messy, but the same thing, this can flip all the way up here, and this can flip into here, and you can multiply those bases. So we get the limit as n goes to infinity, 18 to the n plus 63 to the n over 63 to the n minus 21 to the n. Now this is messy, but all of these are exponential terms. So let's take the largest base in the denominator and do 1 over 63 to the n, 1 over 63 to the n. If we do that, we would get the limit as n goes to infinity, 18 over 63 to the n plus 1 over 1 minus 21 over 63 to the n. The reason we did that is so that these here would have bases that are less than 1. When you have numbers less than 1 and you raise them to higher and higher exponents, they tend to 0. So this is going to be 0 plus 1 over 1 minus 0, which is 1. And all we care about is that it's finite and non-zero, which it is. LCT always requires that this limit comes out as finite and non-zero. If it came out as 0, if it came out as infinity, if it came out as it does not exist, then the LCT doesn't apply, meaning we get no information. In this case, though, we could say by LCT, and since the sum of 7 over 9 to the n converges, so does the sum of 2 to the n plus 7 to the n over 9 to the n minus 3 to the n. So this crazy series, even though we have no idea what it sums up to, we know for sure that it does sum up to a finite value. Don't know what that finite value is. We could figure out the finite value that this one sums up to by using the geometric series formula 1 over 1 minus r, but that formula doesn't apply to this because this is not a geometric series. This is sort of based around a geometric series, but it is not just a single geometric series. I mean, we've got this messy denominator, this sum up top. It's definitely not just a geometric series. It's similar to one, and that's what the LCT does. Now, we're going to investigate the LCT more as we sort of go forward because the LCT basically is sort of the big idea in this whole section. Because what the LCT is really saying is that you can think about these series, because we're thinking about their long-term behavior, about just the parts that matter the most. So we're sort of thinking about what factors are going to be the dominant terms. So as you can sort of see, we basically said this and this aren't going to matter in the long run. Or in this example, we said this plus 1 and this minus 2 aren't going to matter in the long run. Or here, this 5, this n cubed, this minus 1, none of those were going to matter in the long run. The LCT really gets at the sort of heart of the matter here, that we're really interested in what are going to be the dominant terms in the long run. We're going to investigate that more as we sort of move forward, but for now, this wraps up section 11.4, which introduces you guys to the concepts of the comparison tests.